Hi everyone, I'm Chengcheng. Thanks for listening my presentation. Today I will present my work about DNN deployment under accuracy, energy, and latency requirements. DNN is deployed everywhere. It has become a key workload for many computing systems due to their high inference accuracy. Imagine an auto-driving scenario. There's a sequence of input images at camera speed. These images will go through a DNN system, and the inference results will be used for car navigation. We want to get response at camera speed. It should also be very accurate so that the driving is safe. Since it's deployed on the vehicle instead of in data center, it has limited power support. Then with this requirement, how to effectively achieve this? There are two knobs to tune. At the application level, there are many different DNNs to pick from, with different width, depth, and architectures. At system level, different power caps can be set. Different DNN and system settings will offer latency, accuracy, and energy trade-offs. We want to figure out a system which can automatically pick the configurations for every input image so that the three requirements can be satisfied. Unfortunately, there are several challenges we have to overcome. First, the configuration has huge space to choose from. Second, we have to account for dynamic requirement changes and resource contention from co-located jobs. And we also have to make the decision quickly. There are many existing works on improving the accuracy and performance of DNN-inference. They essentially offer more configuration choices in application level, so they are orthogonal to the problem of dynamically adapting application and system configuration to achieve latency, accuracy, and energy requirements. There are existing resource management research. Some of them do look at application and system level together. However, these previous work do not focus on DNN inference systems and cannot address these challenges. To solve this problem, we propose our alert system. At high level, alert works like many existing feedback controller. For every input, it will select a DNN and power cap setting. It will measure how the system performs during the inference. And based on the feedback, it will estimate the latency, accuracy, and energy consumption for the next input under all the different configurations. Based on that, it will pick the best configuration to satisfy the requirements for the next input. And it goes on and on. Of course, Alert has to come up with new designs to tackle the challenges we mentioned. Instead of making separate estimations for each configuration, Alert only estimates one global slowdown factor that reflects the environmental difference between the profiling and the runtime. This handles the large configuration space with low overhead. We also model the global slowdown factor as a random variable to reflect the system volatility. It allows Alert to make aggressive decisions during stable runtime and conservative decisions in volatile environments. We conduct several experiments to evaluate our approach. The experiment result shows that our alert is able to satisfy latency, accuracy, and energy constraints. Our probabilistic design overcomes dynamic variability efficiently. Alert achieves more than 93% of Oracle's performance. Coordinating application and system level improves the performance. It reduces 30% of energy and 27% of error rate over previous work. I will introduce our work in detail with three sections: study and understanding DNN deployment challenges, our alert, a runtime inference management design, and also the experiments and results. Let's first go into the deployment challenges. To understand the deployment challenges, we select 4 popular DNNs for vision and NLP tasks, representing different types of DNNs. We test them on 4 platforms, including embedded systems, CPU servers, and GPU servers. The first question is, what are the trade-offs from DNNs? We test 42 DNNs on ImageNet classifications and show their latency and error rate in this figure. The x-axis is latency, Y-axis is the error rate. We also report a vertex on the convex course. As we can see, there's a huge trade-off. Unfortunately, there's no magic network that provides both the highest accuracy and the lowest latency. In other words, high accuracy comes with long latency. Then was the trade-off from system settings. Given a fixed period of time, we measure the energy consumption under different power settings. Note that after finishing the DNN-inference, the system is still working and consumes energy. We will use color from red to purple to represent power caps from low to high. Here is the setting which consumes the least energy. And here are the settings which finishes computation fastest. We can see that no setting is optimal for both energy and latency. We test how the latency varies across inputs, hardware, platform, and with and without resource contention. For tasks like image classification, the latency variation is tiny across inputs without resource contention. When there is contention, the latency itself and variation across input both increases. We see similar trends for other tasks. Then we claim that latency variation increased by collocate jobs. Then with this trade-off space and variability, what's the solution? We run the ImageNet classification and try to minimize the energy. We examine a range of latency and accuracy constraints, which are the x-axis. The y-axis is the average energy consumption, which is smaller the better. Here we show three solutions, which are the best among their categories. We emulate these oracles from profiling data and assumes perfect knowledge of future. System level is configuring just the system. Application level is just configuring the DNN, and combine both levels. As we can see, combining both levels achieves the best performance. There's a potential of big win. Now we'll introduce our alert design. Going back to the three dimensions, inference deadline, accuracy goal, and energy consumption goal. Alert is able to optimize any one of them while meeting the constraint of the other two. In particular, we'll discuss two tasks: maximize accuracy with energy consumption goal and inference deadline, minimize energy with accuracy goal and inference deadline. Take the maximize accuracy task as an example. It has to pick up a configuration such that maximizes accuracy and meeting constraints for latency and energy. In an alert system, we use power cap as a knob to configure system resources. Thus, the system resource configuration means power cap setting. If we are able to estimate latency, accuracy, and energy for the selected DNN and system resources, it will turn to a full mathematical optimization problem, which is easy to solve. I will introduce how we estimate them one by one in the next few slides. Let's first go to the latency. To solve this problem, there are two key challenges. First, the runtime variation. The same configuration may lead to different latency at different times. Thus, make the static profiling not useful during the runtime. And there are too many combinations of DNNs and resources. We have to predict latency for all these configurations. To address the first challenge about the runtime variation, we use common filter to predict latency. It estimates latency for each configuration using recent execution history. However, it cannot solve the problem. There's too many combinations, and hence will have no recent history to feed into the learner. Assume that we frequently use DNN2 under power setting 1 in the recent history. Then we may know DNN2 takes about 51 seconds to finish under power setting 1. But what about the other power settings? To solve these two problems, Alert introduces a global slowdown factor to capture how the current environment differs from the profiled environment. Such an environmental slowdown factor is independent from individual DNN or power selection. Imagine that DNN2 takes about 34 seconds to finish under power setting 1 during the profiling. At the runtime, due to the computation, it takes 51 seconds to finish. It is a 50% slowdown. Based on this, we predict that all settings are 50% slower than the profiling. With this design, alert make full use of the execution history, no matter which network or power settings are recently used. Using common filter to estimate the mean of latency is good, but not good enough. Sometimes the variation could be very big so that there may not be good prediction. Look at these 3 sequences. They all predict the next input latency to be 50 from the history, but they actually have very different behavior. We do want to differentiate these scenarios as they lead to different implications on DNN selection. Thus, we not only estimate the mean, but also the variation. In summary, we use global slowdown factor to estimate latency. It makes use of recent execution history under any DNN or resources. Unlike the previous work, which mostly only used the mean, we also estimate its variance. Thus, we treat latency as a random variable and estimate its distribution. We will demonstrate how we use this distribution when we talk about accuracy prediction next. Now, with the latency estimation, we are able to predict the accuracy. Given a deadline, the inference accuracy is determined by whether the inference results can be generated before the deadline. If yes, the accuracy is determined by the DNN itself. If not, without any output at the deadline, a random guess will be used as the inference result, which greatly reducing the accuracy, unless it's an anytime DNN. So what is an anytime DNN? Anytime DNN produces complete outputs at multiple intermediate stages. If interrupted, an intermediate prediction substitutes for the originally desired output. On the contrary, the traditional network only has one final output. Assume the deadline arrives before finishing the computation. The traditional network couldn't provide any answer, while the anytime network can still tell the figure is ground. Please read our ICML paper for more details. Now we have a different accuracy-latency relationship. Anytime DNN can provide less accurate results when missing the deadline. With the accuracy-latency relationship and the estimated latency distribution, we treat latency as a random variable and compute expectation of accuracy from it. When the standard deviation of latency distribution is large, the accuracy expectation of anytime DNN would be larger than that of the independent ones, and the faster and less accurate independent DNN would be preferred over the accurate but slow ones. With this mechanism, it naturally makes alerts conservative in volatile environment and aggressive in stable ones. Finally, let's go to the energy. We use power cap as a knob to configure system resources. As we receive the input periodically, we also have to account for the idle power. When the DNN-inference has finished, other jobs on the computer may still consume the energy. When estimating energy, we separate it into 2 parts. The DNN running energy is computed by the power limit, while the DNN idle energy is computed by the idle power. Like the global slowdown factor, the idle power is also independent and estimated by common filter. We use such design as there might be collocated process running and thus affect the energy consumption when DNN-inference is idle. Now we are able to estimate latency, accuracy, and energy for each configuration and turn it into a mathematical optimization problem. Here is our alert system. It takes inference deadline, accuracy constraint, and energy budget as the input. It first estimates latency, accuracy, and energy for all configurations, and then picks a configuration based on estimation and requirements. During the inference, alert measures processing time, energy use, and computes inference accuracy. With this measurement, alert updates the estimation model and loop again. Finally, let's go to the experiment and results. To evaluate our alert, we select two popular DNNs, sparse ResNet and DNN. We test them on both CPUs and GPU servers under 5 different contention scenarios. We evaluate two tasks, minimize energy and maximize accuracy. We also compare alert with 2 oracles and 3 baselines. For the oracles, it changes configurations for each input. We assume it has perfect knowledge of the future, and we emulated it from the profiling result. The static oracle is similar as oracle, but instead it used the same configuration for all the inputs. For the baselines, we use system only, which only adjusting the power cap. Application only, it used an anytime DNN without the power cap. No coordination, it used both an anytime and the power cap. However, these two parts are working separately without coordination. Here is our result summary. All the numbers are normalized to the oracle static. We first evaluate the minimized energy task. From left to right, red represents the baselines. The green is our alert, and blue is the oracle. We also report the violations. As we can see, our alert has close to oracle performance and almost has no violation. Minimize accuracy task, or call it maximize accuracy task, or call it minimize error task, it has similar trend. The baselines, our alert, the oracles, and the violations. Finally, let's look into the different dynamic behavior of our alert. This figure shows how alert works with the traditional DNN when environment changes. The orange curve is the alert with traditional network only, and the red line is the constraint. At the beginning, there's only one process for DNN-inference. It always meets the latency deadline. The power is right beneath the budget, which means that we make full use of the power budget. And because the runtime variation is relatively small, alert always selects a large but accurate DNN. Now contention starts. A memory-intensive process competes the resources with the inference task. Look at this sudden accuracy drop. The collocate process launches during the inference, so this inference task becomes super slow. We terminate it when the deadline arrives, even though there's no available result. Fortunately, alert quickly detects these changes and reacts to the large runtime variation. It switches to much simpler but faster DNN under the highly dynamic environment. The switch reduces deadline misses, which is super great. But sometimes it's too conservative. It wastes a lot of time budget and thus has an accuracy loss. Now the contention ends. Alert switch back to the high accuracy but larger DNN. Now we demonstrate how alert work with both anytime and traditional DNN under the same experiment setting. It is shown in the blue curve. Unlike the previous result, in the volatile environment, alert switched to anytime DNN to ensure a result before the deadline, making use of the anytime behavior. Alert is able to achieve high accuracy before the deadline. Overall, alert is conservative in volatile environments and aggressive in the stable ones. We also evaluate each component of alert separately to show the effectiveness of our design. Please check our paper for more details. In summary, this work focused on DNN-inference, which is common but hard to manage. We first conduct experiments to understand the challenge. Then we design our tool Alert, which dynamically selects DNN and system resources to meet latency, accuracy, and energy requirements. We evaluate alerts with a variety of workloads and DNNs and achieve high performance and energy efficiency. That's all. Thanks for your listening.